Do you guys hear me? Anyone? Good morning. We are going to continue regarding the consecutive reactions in which we have been talking about the multiple reactions of series reaction mechanisms. Here, the multiple reactions were the series reaction. If A gives R, so R is an intermediate, and this R gives S. So A gives R as an intermediate, and the R again converts into S. So when we looked at this stage, if you take it in the concentration versus time, the A keep on increases, and the R starts from here. This is CA at this point, and the R increases to the maximum at one particular place, CR max, and again it goes down, okay, because this is because your S formation. So the S started to occur at a higher rate when the time is maximum. So this is the T max. So at the T max, you get then the maximum intermediate. Once you get the maximum intermediate, then like automatically your concentration of S keeps on increases drastically, and you convert into as a product, desired product as S. So this is what the actual thing. And here now, the question is about the same thing. It says consider a consecutive unimolecular first order type reaction. Consider a consecutive unimolecular first order type reaction such as A gives R, R gives S. Okay, which occurs in a mixed flow reactor, which occurs in a mixed or occurring in a mixed flow reactor. At time t equal to 0, Ca equal to Ca naught to 0. So this is what it's given here. And it says find the maximum concentration of R and the time when maximum concentration reacted in M of R. Find the maximum concentration of R and the time when maximum concentration reacted in M of R. This is nothing but here it says it is a tank reactor where you supply the particular feed A and you have to get S. But in this case, you also get a smaller smaller R, that is the concentration of R will be less and the concentration of S will be higher in this case. So this is what it shows. So now we need to find the maximum time too. So that means what is the time here? The time indicates the residence time. Okay. So the residence time and the holding time. Holding time means it's, so this is also called the holding time. Holding time means the time taken by a reactant or a feed in the tank is the holding time. Okay, so this residence time and the space time, the time required to process a one reactor volume at a specific condition in the reactor. Okay, so that is the space time. These two are supposed to be same. That means T equal to tau. So this is what you need to remember now. Because always in the tank, we consider this is an ideal mixed flow reactor. Sir, audio video clear ka? Divakar. Ashwin. Ashwin. Balasweta. Sir, anyone have problem in audio and video? Okay, now we again come into this picture now, and the space time and the residence time in the mixed flow reactor is same here, because the whatever it comes in, and we consider this as an ideal mixed flow reactor. That means there is no stagnancy, there is no purging, or there is no bypassing here. Okay, so in this case we consider as an ideal reactor. That means the reactant which enters into the reactor, it spends the same time as like all the reactant, and then like it leaves in the reactor. Okay, this is what the idealness here. So that means the time t will be, or the residence time will be same as the space time here. Okay, so this we need to remember it here. Okay, now we need to consider now this is an like MFR. So we need to consider the performance equation here, and then we start to write about what is CA, because we need to find CA here, CR and CS. Okay, this is what. So these three has to be found out here. Okay, for that we use a performance equation. Here is the minus equal to accumulation. So the accumulation will be 0. So that means the input. So here the input is the actual flow in FA naught. And here it is a disappearance. So it is minus RA into V minus FA equal to 0. This is what the actual or this will be in the minus. Okay, so this is what the actual performance equation. So FA not equal minus FA equal to minus RAV. Now what is minus RA, that you need to know. So before we take into minus RA, the FA can be written as volumetric into the total concentration, volumetric flow rate into the total concentration, volumetric into the outlet concentration. Okay, so CA naught minus CA by B. So this no, we'll take it minus RA equal to V by V naught or V. So this will be tau V by V naught. Okay, this is the volumetric flow. This is volume of the reactor, and this is volumetric flow. So this is the actual performance equation for the mixed flow reactor that we used to derive before. And now from here, what is minus RA? Equal to K1 CA, because K1 CA, this is what the A had to do. And you put this one, this is 2, substitute 2 in 1. So tau equal to CA naught minus CA by K1 CA. So what we need? We need a CA. K1 tau plus CA equal to CA naught. So CA equal to CA naught by K1 tau plus 1. So this is what the concentration of the outlet A. So this we keep it 3. So you can even directly start from the performance equation. So I just derived the performance equation here, and from this, if you see the performance equation, tau equal to CA naught minus CA by minus RA. So minus RA can be K1 CA. So we consider this is a first order. Okay, and This one can be written as Ca equal to Ca naught by K1 tau plus 1. Okay, this is what the for A here. For A. For A, this is the the derivation. And the next we go for the CR. Because we completed CA now, now we go for the CR. What is CR here? It is again same like the previous one. CR will be same like previously, like and this time it is a rate of appearance, so it will be in the plus cell. That means it will be in the so the rate of appearance will come in this side. That means it is minus RR into V equal to CR. So if you take it in the way, if you take this side, CR minus CR naught equal to minus RR V, and if you consider this, CR minus CR naught by minus RR equal to V by V naught equal to tau. So again, this is a tau for, this is the same tau, okay? And now, what is minus? Oh, this is actually now plus set. It's not minus. So, because it's the rate of formation. So, RR will be your K1CA minus K2CR. This is what the rate expression that you can write for the intermediate. K1CA, that is the formation of CA. R and the disappearance of R. That is what the formation of R and the disappearance of R. So you substitute this here. This is 4. This is 5. Substitute 5 in 4. So we get tau equal to CR minus CR naught by K1 CA minus K2 CR. So now we need to find what is CR. CR equal to because CR naught is a 0 here. So that will be, that we need to consider it here. And CR will be equal to tau K1 CA minus tau K2 CR. And you bring this here, and that will be CR 1 plus tau K2. And here you substitute tau K1 CA. This is maybe 6. So substitute 3 in 6. Substitute 3 in 6. So CR equal to CA naught or we say CA naught. Yeah, this, if you substitute CA naught, then K tau K1. So CA naught tau K1 divided by 1 plus tau K1, 1 plus tau K2. So this is our CR. This is 7. Okay. So now we found CA and CR. Then it is very easy to find CS now, because CS is nothing but CA naught minus CR CA. So I just wrote this one, and we only want to find CS. CR equal to CA naught minus CR CA. So that means substitute. This we take it as 8. Substitute 3, 7 in 8. So then you get, sorry, CS here, right? So CS will be, you substitute everything, you get like an, so this will be like this. So CA naught. If you do all the substitution, everything, the final form, I just write only the final form here, and it will be like a tau square K1, K2 divided by 1 plus tau K1, 1 plus tau K2. So this is the CS. Okay, like this. Now we found all CS, CR and CA. So what they asked there? They asked about to find the maximum. To find the maximum concentration of R. That means you have to find CR max and tau max. To find CR max and tau max, it's very simple that you need to differentiate the CR. That means dCr by d tau has to be 0. That he has to do it from in equation 7. If you differentiate the R with respect to time, so you consider that as a 0, then you get a tau max. So the tau max will be something like it has to come like this: 1 by K1, K2. This is 10. So if you differentiate the equation 7, if you differentiate with respect to tau, CR by tau, I mean d tau equal to 0, because you want to find the maximum point. As I said, the graph goes up and comes down, right? So the uphill region, that is the point where it goes up and then move down a hill. So that point can be identified if you differentiate with respect to the x-axis, that is dy by dx in the mathematical expression. If you have the graph at dyx, if you go up and come down, if you want to find this point can be say as dy by dx equal to 0. That is what the mathematical discussion. Okay, so similarly here, dCr by d tau equal to 0. So if you do it, you can get the tau max. Once you get the tau max, you substitute this tau max here in equation 7, then you get the CR max. You substitute. Now I just go with the next point. So substitute 10 in 7 as CR equal to CR max. Then you get a CR max will be as a CR equal to CR max and tau equal to tau max. Or they will, sometimes they will call tau optimum tau or the optimum space time here. Okay, if they say, then they will put as a tau opt, tau opt, or you can put the tau max and tau opt, like everything is same here, so you don't need to confuse here. So CR max will actually something you get as CA naught by 1 plus 1 by K1 plus 1 by K2. This is what you will get, sorry, K1, K2, K1. So this is the final answer that you will get for CR max. CA naught by 1 plus K2 by K1 plus K2 by K1 root. Maybe here there is a 2, I missed it. Plus 2. So this is what the final answer you will get for this particular estimation of the maximum R and the maximum tau. So here the 11. So the 11 and the 10 value is our actual requirement here. So depending on the optimum time, optimum space velocity, the maximum R can be calculated here. And this maximum R has to be maintained to get to actually get a higher rate of product formation. So this is what the serious reactions are actually involved in like identifying the optimum condition in a reactor. If you have any doubt, we can discuss, sir. Just put it on now. Sorry, any doubt that you need to clarify now? So to make it very clear here, that you need to, if you draw the graph, you will easily identify that. So the concentration and the tau. So now I put tau here, and the concentration of A or yes. So at this point, so this is your CR max, when tau max, or we say tau optimum. So at this particular space time, so what it means that for this reversible reaction, you need to run the reactor flow rate. I mean, the flow rate of this particular reactor has to be run according to this particular tau optimum condition. That means this is the flow rate for this particular reactor, so that you will get the maximum R. Once you get the maximum R, then the rate of formation of S will be higher in this case. Okay. So that's why we actually calculate here. So with this, we actually complete the 4th unit, and now we are actually moving towards the 5th unit. The 5th unit covers mostly about the temperature and the pressure conditions that exist in the reactor. That means the effect of temperature and pressure here. In this whole unit, we are going to talk about how the temperature and the pressure effect in the reaction and also in the reactor. Both cases we need to identify. Before we go into this topic, we need to know what is the actual reaction and what is exothermic, endothermic, why the heat capacity plays a crucial role here. Because in general, if you want to find the heat enthalpy change in case of in a particular vessel or anything, you put delta H. Delta H is you take a tube, you give some heat H1 and you get H2 because the heat started to liberate out. Okay. So this actually we say steam. You supply a steam in a pipe and the heat started to eject out there. So this delta H is your H1 minus H2. So this will be actually written as mass Cp T1. So we say this is T1 and this is T2. T1 minus T2. This is how the simple calculation of the enthalpy that we write, okay, in a particular system. But here we consider this is a steam. But you know that if the temperature change for the steam or for water, the specific heat capacity will also have an effect by the temperature. So sometimes they will write this as a delta Cp. So this delta Cp can be represented in a way of, for example, alpha plus beta T plus gamma T square, like this. It will keep on going. So with respect to change in temperature, the property of the particular substance which transfer the heat will also have an effect. So there is a possibility to have a delta Cp, but in general, if you are going with a higher heat transfer system, you consider the heat capacity is same for whole system. But in the reactor, when you have a change in enthalpy, but you try to keep the temperature constant. If you try to keep the temperature constant, because it's a closed system, in the closed system, the temperature will be maintained accordingly. If the temperature maintained, then the pressure has to be maintained. If these two are maintained, then the specific heat capacity will change. Why? Because there will be change in its phase, or there will be change in its property, because you are trying to put the system in a closed system and you don't want to you actually don't want to expose to the environment. If you don't want to expose to the environment, then the system will be packed inside. So this system or a substance which is packed inside does not have any chance to escape. So in that scale, you try to keep the temperature and the pressure constant. As you know, PV equal to nRT, so that means pressure is proportional to temperature. If you maintain the temperature, then the pressure is also maintained. But the condition inside the system might change because you get some product formation. If the system or substance try to change in a different position or in its different shape, then the specific heat capacity will definitely have an impact by the temperature. So this is the actual thing that you need to remember in the reactor, in case of reactor, because in a closed system. So before we go into this, what is an exothermic? What is an endothermic? This, I guess you are keep on discussing this every time, and you take an energy here, and this is the path. So that means if A converts into B, this is the process here. We take it here, A gives P, and P gives Q. There is two different conditions. I mean, the reaction mechanism that we are taking as an example here. And at particular potential energy, because every molecule and its rest condition, it has a certain potential energy. So that particular potential energy is this. So you consider this as the particular energy where the A is at the rest. It does not have any change in its impact. And you try to change its condition, or you try to you put this A into a reactor and you change the condition to convert into B. So what you do that, you try to increase its energy. So that means if you see the Morris chart, Morris diagram, we might talk before. The Morris diagram, you have a stand still and you have another component, you put it closer together, the potential energy drastically changed, and that will give a lot of vibration. Okay, similarly, you try to change the condition so that the energy will start to increase. That means the molecule vibration is too high here. And at particular stage, you reach an intermediate I. Okay, at this point, it is called an active complex site. That is a transition complex. You can call in any name, or you can say ions, or you can say radical or anything. Okay. So when you reaches this particular position, then this particular energy level is the activation energy. This is the activation energy. That means the minimum energy requirement to initiate the reaction. So once you reach here, the reaction started to initiate. Okay. Once you actually reach certain position, then it will try to convert into product on its own. So you don't need to do anything after this. So this will start to push to a certain level, and you get a B here. So if you see the level where the energy level of A and the energy level of B. Here the energy level of A is lower than the energy level of B. That means some energy is being gained by this particular product during this experiment or during this the reaction mechanism. If it gain, then it's a endothermic because it actually absorb endothermic reaction. It tries to absorb its energy into the system. Similarly, you start with the P here, somewhere here, okay, and you go with until the initial stage, and suddenly it drops drastically to form Q. At this point, Q is formed. So you see the actual energy requirement of a P, it is higher than Q. That means it liberates heat. Some of the heat being liberated out into the system. So it is called a exothermic. So if you do an enthalpy calculation here, then you get a, if you say H1, H2, then you get a plus delta H value here. So if you put plus, then it's an exothermic. If you say same H1 and H2, because the product is H1, we consider, then we say delta H. So there is an heat is being like liberated out in the system. So that is what the exothermic is. So this is the major thermic concept that we understood from here in the reaction mechanism. With this, we calculate the endothermic, that is the heat which is being absorbed in the system, and here the heat which is being liberated from the system. Okay, this we actually keep in our mind. Then we started to write the enthalpy calculation for a reaction mechanism. This is what your 5th unit consists of. Okay. In the 5th unit, it is actually going to be a very simple thing. So only a few problems, few different types of problems that we are going to concentrate. And you always remember that the heat which is absorbed in the system and the heat liberated in the system has to be calculated in your reactor, because the actual energy requirement in the reactor, it is not only to maintain the temperature, it is to maintain the pressure. So for the both cases, you need to know whether the system is an exothermic or an endothermic inside the reactor. Okay. So if you have any doubt, we can discuss. We have another 3 more minutes.